This is lecture 12 part 2. In last lecture we have discussed what is realization problem, and we found that improper transfer function cannot be realized. So today we'll be solving some numerical problems. From there we'll learn some canonical structures. So that is that realization problem. So realization problem is that whenever a transfer function is given, you need to find state space matrices. So this particular problem is called realization problem. And improper transfer function cannot be realized. So this thing we have discussed in detail in last lecture. So today we'll be solving some problem. So this is example 1. So suppose a transfer function is given, that is gs equal to 1 by a square plus 5s plus 6. So you need to realize this transfer function. So as we know that transfer function, that is output by input. So from here we can write that a square ys plus 5 plus 6 equal to us. We have just multiplied and if the Laplace transform of this ys is this one, so that means we can write that this is d2y2 dt2 plus 5 dyt by dt plus 6 yt is equal to ut. That means if you have this differential equation, then if you take Laplace transform, you will get this one. So now we need to define state variables. So as the order of this differential equation is 2, this is the second order differential equation. So we need 2 state variables to describe that system. So let us define the state variables. Let yt equal to x1 and x2 equal to x1 dot. Here I want to mention one particular terminology, that is called that phase variable. So one state variable is the time derivative of the other state variable. Whenever one state variable so here you can see that one state variable, that is say x2, is the derivative of other state variable, is the derivative of the other state variable, then they are called the phase variable. So what is phase variable? Whenever one state variable is the time derivative, so it would be better if we write that this is time derivative of the other state variable, then it is called phase variable. So here you can see that we have defined that yt equal to x1, and then you can see that x2 is the derivative of the other state variable. So this is phase variable. So now if we proceed with these state definitions, so then what will you get? So x2 dot, from here we can see that x2 dot means d2y by dt2. So we can have that x2 dot equal to minus 5. So dy by dt equal to x2 minus 6x1 plus u. So all are actually function of time. I am not writing so explicitly, but it is function of time. That is x1 dot t equal to x2 t. So if we write it in matrix form, what will we get? So suppose x1 dot x2 dot. So we have that state vector x1 x2, and here we have that input matrix. So x1 dot equal to this one, and x2 dot equal to minus 6x1 minus 5x2, and here you have 1. And what is your output matrix? So output matrix y, here you can see we have defined that yt equal to x1. So your first state variable, that is 1 0 x1 x2. So this is your output equation. Now you can find some interesting relationship with that poles and eigenvalues of that A matrix. So here we get that this is your A matrix, this is your B matrix, and this is your C matrix. And here you can see that D matrix equal to, so D into U, so here D equal to 0. And whenever you have a transfer function, if it is strictly proper transfer function, then the D would be equal to 0. So D matrix is basically whenever you find that whenever you put in this transfer function S tending to infinity, then that value would give you the D matrix. So here if you put S equal to infinity, S tending to infinity, then you will get D equal to 0. So in case of strictly proper transfer function, always you would have D equal to 0. But if you have a biproper transfer function, then you would have some D value. Here, if you look at the transfer function, so what are the poles? So if you just factorize this one, so you can write that this is S plus 2, S plus 3. So the poles of that systems, poles are minus 2 and minus 3. From here you can see that this is minus 2 and minus 3. So interestingly, if you find the eigenvalues of this A matrix, so what will you get? Eigenvalues of matrix A. So eigenvalues of matrix A, if you find that one, so you know that the determinant of lambda I minus A, so as it is 2 cross 2 matrix, so then this identity matrix would be 2 cross 2, so that means lambda 0 0 lambda, the first one lambda into I minus A. So A matrix is here, that is 0 1 minus 6 minus 5, 0 1 minus 6 minus 5. So if you take this one, this is lambda minus 1, then 6, then lambda plus 5. So that would be equal to 0. The roots of this equation, that is called the characteristic equation, are the eigenvalues of that matrix A. So that would be lambda into lambda plus 5 plus 6 equal to 0. So from here you can have that lambda 1 equal to minus 3 and lambda 2 equal to minus 2. So this is very interesting result in state space theory. So eigenvalues of the matrix A are the poles of that system. So you can see here the poles are minus 2 and minus 3, and after state space realization you would have, this is that A matrix, this is B matrix, and this is C matrix. But if you find the eigenvalues of that A matrix, it gives you the poles of that system. So this is very important result in state space analysis. So that I can write that eigenvalues of A are the poles of GS. So that means if a system is realized and it is given in state space form, and if you are asked to find what are the poles of that system, just find the eigenvalues of that system matrix, and those are the poles of that system. So now we'll see some more examples on realization. So here we have another example. That is, if you have a transfer function, so that is ys by us, that is 2s square plus 2s square plus s plus 5, and here s cube plus 6x square plus 11s plus 4. So this is a transfer function and we need to realize it. So here I will be showing you two spatial structures of that realization. They have some names called controllable canonical form and observable canonical form. So those are the spatial structures of the state space matrices. But here I would like to point out, whenever a transfer function is given to you and you are asked to realize it, you can find any structure. But here, to just learn those two specific structures, I am just realizing this particular transfer function in those specific structures. But it is not mandatory that always you need to realize this transfer function in that structure. You can do it in any arbitrary structure. But if you are asked to do it, you need to follow this particular technique. So here, the order of the degree of the denominator polynomial is 3. So in your first step, you need to divide that numerator and denominator by that maximum degree of the denominator. So if you divide this numerator and denominator by s cube, then what will you get? So that means if you divide by s cube here and here, so then you will get that 2 s minus 1, that is 1 by s, 1 by s square plus 5 s minus 3, and here you have that 1, then 6 s minus 1 plus 11 s minus 2 plus 4 s minus 3. So we have divided numerator and denominator by that maximum degree of the denominator, that is s cube, and then you can multiply numerator and denominator by one Laplace transform variable xs. So now if we do like that, so we have that ys, you can see here that ys, you can equate that numerator, so that ys equal to 2 minus s to the power minus 2, then 5 s to the power minus 3 into xs. So this one we are equating that numerator, and if you equate the denominator, you would have 1 plus 6 s minus 1, 11 s minus 2 plus 4 s minus 3 xs. So we have two algebraic equations. So now we can write this algebraic equation in this particular form. You can see here, if you multiply this xs here, so then from here you can write that xs equal to us minus 6 s minus 1 plus 11 s minus 2 plus 4 s minus 3 xs. So just I have rearranged this particular equation and I can write it in this form. So now if I do like this, then what happens? We have two algebraic equations, and now we will be realizing these two equations in that state diagrams form. So that is, you can see here that xs, here you can see that xs is equal to minus 6 s to the power minus 1 xs, again minus 11 s to the power minus 2 xs, and 4 minus 4 into s to the power minus 3 xs plus us. So if we take a node here, say suppose I take a node here, and that is say xs. So then we can see here that if we have one node u here, so then x equal to, you can see here x equal to u, then we should have some node here, here, and here. If we multiply with s to the power minus 1, that means one integrator, and there is another integrator, So just what I am trying to do, I am just trying to realize this one in state diagram, that is that signal flow graph. So here you can see that x, this node is indicated by x, this one. So x equal to u, then you can see here minus 6 s to the power minus 1. So minus 6 x to the power minus 1 means, so here if I just make one loop here, that is if I say that this is minus 6, so then you can see here x, you can see here this signal is going and again coming back here. So that is x equal to minus 6, here minus 6 s to the power minus 1 into x. So the first term we get. What about the second term? Minus 11 s square. So now if you come to this particular node, then you can see that here that would be s to the power minus 1 into s to the power minus 1. So that means double integrated 1 by s square. So 1 by s square term here, and then if you just close this loop with the gain minus 11, so then you can see here that we have this loop, that is minus 11 into 1 by s square into xs. This is done. Then what about the third one? The third one is s to the power minus 3. So that means we have one more path here, and the gain is minus 4, and you can see here that we have s to the power minus 1, s to the power minus 1, s to the power minus 1. So that means s to the power minus 3, and this is that loop. So then we have realized this particular algebraic equation. Then we need to see this equation. So ys equal to, you can see here, minus 5 into s to the power minus 3 into xs. So then you can see here that if I take one node here, and if I just make a path here with gain 5, then you can see here that minus s to the power minus 1, s to the power minus 1, s to the power minus 1 into 5 into xs. So that means if I reach here, and if I say that this point is y, so then we can have this term. Then similarly, what about that s to the power minus 2 into xs? So that means if you take from here, there is a branch with gain 1. So you can see here that you are starting from this point and going like this. So then it is s to the power minus 1 into s to the power minus 1. So that is s to the power minus 2 and branch gain 1. So that means this is that branch gain. So that means the second term is realized. And what about the first term, that is s to the power minus 1? So that means start from here, we have this one, that means just only this branch, s to the power minus 1 into 2. Then we have that y. So interestingly, what we have seen, we have this transfer function, then divided numerator and denominator by that maximum degree of the denominator, and then we get this particular expression. Then if we equate the numerator with this numerator, we have this relationship, and if we equate denominator, then we get this relationship, and then we have rearranged this denominator equation, and finally we get this particular algebraic equation and this algebraic equation. Now we have realized these two algebraic equations in the state diagram form. So now if we just define that this x as that x3 dot, then x3 dot, if we take integration, so here you can see that we are integrating this because this is that arrow signal, so we are integrating this one. So basically we will be getting x3, and now in phase variable form we are defining that x2 dot equal to x3. Then again in the same way, as x2 dot is integrating, that is h to the power minus 1. So we have another state variable, so that is x2, and we are defining that x2 equal to x1 dot, and again there is one integration here. So then we are getting another state variable, that is x1. So here we have defined like that there are three state variables and they are in phase variable form. So just from this state diagram we can write that x3 dot this one here, x3 dot equal to minus 6x3, you can see here minus 6x3, then minus 11x2, then minus 4x1 plus u. So this is one state equation, just directly I have written from this diagram. Then we have x2 dot equal to x3, and we have x1 dot equal to x2. So we have three state equations. And what is your output equation? That output equation y equal to that 5x1, then you can see here that is 1 x2, and here you can see that 2 x3. This is that output equation. So if you write these particular set of state system equations in matrix form, what will you get? Say x1 dot, x2 dot, x3 dot, you can follow any sequence as I have pointed out earlier, that is x1, x2, x3, x1, x2, x3, and here you have that input matrix U. So x1 dot equal to x2, that is 0, 1, 0, and here 0, and x2 dot equal to x3, and x3 dot, this equation you can see here, that is minus 4, minus 11, minus 6, and here you have 1, and output is this equation, that is 5, 1, 2. So interestingly, you can see here that the 1, 1, this is coming in this form, and here you can see that A matrix has a special structure, and here this minus 4, minus 11, minus 6, they are actually the coefficients of that. You can see here minus 4, minus 11, minus 6, they are the coefficients of the denominator polynomial, and here particularly 1, 1, this particular structure would come, and in the B matrix you can see all elements would be equal to 0 and the last one is 1. So AB matrices, they have that special structure, and this particular structure, this particular realization is known as controllable canonical form, in abbreviated from CCF. So this is one realization. This is one realization where A and B matrix, they are in special structure, but C does not have any special structure. So this is that method we have followed. That means whenever a transfer function is given, we get these two numerator and denominator in these particular structures. From there, I have drawn that diagram, and I write this state equation, system equation and output equation. And in the system equation, you can see that A and B, they have some special structure. This particular realization is called that controllable canonical form. So we again realize, as we have already discussed, that means the state space realization is not unique. So we can also realize this particular transfer function in different form. So let us see. So here, suppose you know that same transfer function is given here, that is ys by us. So that is 2 square plus s plus 5 and s cube plus 6s square plus 11s plus 4. The same transfer function we are taking, the same transfer function. So now the method is you need to divide numerator and denominator by that maximum degree, that is s to the power 3. So if we do that one, then we have s to the power minus 2, 5, s to the power minus 3, and here we have done it earlier. So here the difference is we are not going to multiply numerator and denominator with a variable x. We are not going to do that. So now after dividing the numerator and denominator, we are just multiplying and getting that this particular relationship. If you multiply, cross multiply, so then you will get that ys this term. We are multiplying this term with ys because cross multiplication, and it would be ys plus ys into this term. So if we are taking the rest of the term on the right hand side, and if you cross multiply this term with us, so we get that us, so that is 2 s to the power minus 1 plus s to the power minus 2 plus 5 s to the power minus 3 into us minus the rest of the term means here rest of the term is 6 s to the power minus 1, 11 s to the power minus 2 plus 4 s to the power minus 3 into ys. So this algebraic equation we have, we get it from this transfer function. So the difference with the first one is here we are not multiplying with x's. So now we are just trying to realize this algebraic equation in state diagram form. So let us see. So if we start with node, say suppose here you can see that ys is, that is 2 into s to the power minus 1 into us, s to the power minus 2 into us, and again here you can see there would be some feedback, that is minus 6 s to the power minus 1 into is, minus 11 s to the power minus 2 into is, like that. So if we take that node here, so suppose this is y, so if you just multiply with 1, you have that y, that is output node. Then you can see here that if you just multiply with s to the power minus 1, and if you just make that feedback loop here, that is minus 6. So you can see here, so if I write minus 6 here, minus 6, you can see here this y equal to minus 6 into s to the power minus 1. So this term is done. So now if we take a node here, just multiply with 1 and put another integrator here, s to the power minus 1. So then you can see that the second term that is minus 11 s to the power minus 2. So here, like previous example, here if we just put minus 11, then the second second term is satisfied. That means you start from here and it is coming, and 2, you can see here h to the power minus 1 and h to the power minus 1. So that means h to the power minus 2. So the second term is satisfied. Similarly, we take that one more node here, just multiply with 1, and here you just introduce another integrator, and we are just trying to realize the third term. And here you can see, if you just make this loop with the gain say -4, so then the third term is satisfied, because here you can see h to the power minus 3, here h to the power minus 3 are there. So now we are going to realize this part. So now if we take one node here, that is 1, and here you have that input node u. So the first one is 5 into h to the power minus 3. So if I just multiply here with 5, so then we can see here that 5 into h to the power minus 1, h to the power minus 1, and h to the power minus 1. So that means y equal to 5 h to the power minus 3 into us. The first term is satisfied. Then what about the second term? For second term, you can see here that h to the power minus 2. So that means if I just make a loop here, if I draw a branch here with gain 1, so then you can see that u is coming here, and then it is passing like this. So it is taking h to the power minus 1 into h to the power minus 1, that is h to the power minus 2 into u. And what about this term? So this term you need to just draw another branch that will be taking only, so we'll be taking one branch that would be taking only 1 h to the power minus 1, this one. So this gain is 2. So then you can see here that this particular term is satisfied. 2 into, so it is starting from u, so it is going like this, that is this path, it is following like this, and it is going like that. So that means 2 into u into h to the power minus 1. So this is done. So we have realized this particular equation, algebraic equation, and this is that realization. And here we can see that if we just define that this is x3, the state variable, and so that one should be x3 dot, because if this is x3 dot and if it passes through this branch, this is one integrator, you will get x3. And again we are defining that phase variable. So then you can see here that x3 equal to x3 dot equal to x2. This is in phase variable form. It is indicated by this particular branch. Similarly, if it is x2, then here it would be x2 dot, because this is that integration. And similarly, that one would be x1 equal to x2 dot, and here you have that x1 dot. So this is actually that realization. And now let us see, if we just write this particular state diagram in that equation form, what relationship we would have. So that is x3 dot, let us see, x1 dot, I am writing this one. So x1 dot equal to 5u, this part, and then minus 4x3, this branch. Now x2 dot, here we are just concentrating at that node. So x2 dot equal to, here there is one branch, that is u minus 11 x3, and we have x3 dot, that means here at this particular branch x3 dot equal to, here we have one branch, that is 2 into u, so 2 into u. So here I think x2 dot in this case, that would be equal to u, and here that is 11 minus 11 x3, and here we have another one, that is x1. So here you see x1 is coming here, so that means we have x2 dot, that is plus x1, and x3 dot equal to, you can see that x2 here, say x2 minus 6x3 plus this branch 2u. So we have these three state equations, and here you can see that y equal to x3. So this is x3 dot, so basically that one would be x3, so y equal to x3. So now if you write these three state equations, then what will you get? So this is x1 dot, x2 dot, and x3 dot. We are just writing it in matrix form, x1, x2, and x3, and then you have u. So x1 dot equal to 5u minus 4x3, then x2 dot equal to 1u, so minus 11x3. Here we have that x1, and x3 dot equal to x2 minus 6x3 to u, and what is your y? Y equal to 0, 0, 1, and here you have x1, x2, and x3. So interestingly, you can see here, this is another state space realization where your A matrix has some specific structure, and this is your B matrix, and this is your C matrix, and here you can see that A has that structure, that means here you have 1, 1, and all coefficients are here. So in the above state space realization, you can see that your 1s are here, and these are the coefficients, and B matrix all zeros, and the last one is 1. But here you can see that C matrix has some structure, all zeros, and last one is 1. So this particular structure is called observable canonical form, OCF, observable canonical form. So what we have seen, whenever we have one transfer function, some transfer function is given, so we can have that realization because it is a strictly proper transfer function. We can have realization. So any realization we can have, but in this particular example, we have seen two specific realizations. One is that controllable canonical form, CCF, this one, and this is observable canonical form. So from here it is clear that, you know, for the same transfer function we can have many realizations. So here we have two realizations, that is CCF and OCF. So CCF and OCF, they have some specific structures. So these are the structures. So I would suggest you all to solve some problems, because here for getting CCF and OCF, you need to follow this particular method so that you can have it. So this is all about that realization. So there are some other canonical forms like the diagonal form. That means that A matrix, system matrix, would come into the diagonal structure. The second form is called that Jordan form. So those are, I'm not going to discuss so those canonical forms, but there are some specific realization. So those who are interested, you can see, but I'm not going into that detail. So here what we have discussed, that means what is realization problem, and improper transfer function cannot be realized, and we have just discussed two examples. In first example, we got one realization, and from there we found that okay, so eigenvalues of that system matrix are the poles of that systems. And in the second examples, we found that we two separate realizations for a given transfer function. One is controllable canonical form, another one is observable canonical form. So now we will discuss what is that linearization of nonlinear system. That is that linearization of nonlinear system. So a nonlinear system, so far we have discussed that linear time invariant system. So now I'll be giving you some idea whenever a nonlinear time invariant system is described by a state space equation, then how to linearize it. So let x dot t equal to f txt, where xt0 equal to x0. So here first I am just going to introduce a concept called that equilibrium point. That means whenever you have a system, dynamical system, then it has some equilibrium points. That means whenever some input is applied to that system or when time evolves, if there are some points, that means there are some operating points where the derivative of the states is equal to 0, that means that system would stay there. So if you just apply an input to that system may be somewhere in the state space, but when input is applied, it may go to some point and it would stay there. And why it would be staying? Because at that point the derivative of all the states would be equal to 0, and that point, if it is stable, then it would be there. If it is unstable point, whenever you apply some inputs or if you give some perturbation, that system would be shifted from that point to some other point. So that is actually that concept of that nonlinear system stability concept. So I'll be discussing those things later. So for the time being, I'm just going to give you some definition of the equilibrium points. So let x dot t equal to f txt. This is that dynamical equation. This is the dynamical equation, general dynamical equations, and this is that initial condition. And here I am just taking the time t, so that is t0 to t1. So in that interval, and then a point. So point means this is actually a coordinate in state space. A point xe, suppose that is d is the state space, is said to be an equilibrium point. This is very important in case of nonlinear systems. Equilibrium point at time te if f t xe equal to 0 for all time greater equal to te. So what is that? That means whenever your system, so here you can see that in place of xt I have just replaced xc. So then this xc is said to be one equilibrium point whenever this equation is equal to 0. So this one is equal to 0 means, so this x dot t equal to 0. So as I have pointed out, that means equilibrium point is the point where the derivative of that state would be equal to 0. So this is actually the definition of that equilibrium point. So let us see some example, then I think it would be clear. So suppose you have x1 dot equal to x2 and x2 dot equal to minus epsilon x2 minus g by L sin x1. So from this state equation, it is clear that it is not a linear system. It is not a linear system because here you can see that this term is there, sin of x1. So you cannot write in that particular form that x dot equal to x plus bu. In that form you are not able to write. So now this is a nonlinear systems and we are interested to find what would be the equilibrium point. So find equilibrium point. Find equilibrium point. How will be finding that one? So from definition we have seen that in the equilibrium point that x1 dot and x2 dot would be equal to 0. So x1 dot equal to 0 means x2 would be equal to 0 and x2 dot equal to 0 means that minus epsilon x2 minus gl sin x1, that one is equal to 0. So now at equilibrium point x2 equal to 0 means this one equal to 0. So this term is equal to 0. So that means sin x1 is equal to 0. So x1 is n pi, where n equal to 0 plus minus 1 plus minus 2. So now from this particular example, what we have seen, we found that in this particular nonlinear system, there are infinite number of equilibrium points or many equilibrium points. So here you can see that equilibrium point is, say, one is x1, so that is 0, 0, x2 equal to 0. Another one is plus 1, 0, minus 1, 0, plus, so not plus 1, that is pi 0, then minus pi 0, plus 2 pi 0. So there are many equilibrium points. So from this particular example, we have seen that how to find the equilibrium points, and you may have some nonlinear system which may have many equilibrium points. Many equilibrium points. So now let us see one more example. Say suppose you have a dynamical systems that is 2 plus sine x1 plus x2. This is obviously a nonlinear systems. 3 minus sine x1. So now what would be that equilibrium point? So here you need to write that x1 dot equal to 0 and x2 dot equal to 0. Now look at here. If you put, sorry, so this is x2. So now if you put x2 equal to 0, x2 equal to 0, so sine x1 equal to 3, then you cannot have any value of x1, so that sine x1 would be equal to 3, because sine x1, it varies from plus 1 to minus 1. So that means in this particular case, no equilibrium point exists. So this is very important. So in first case, what we have seen, in first case we found that whenever a nonlinear system is given, many equilibrium points you may have, but here this is a case where there is no equilibrium point. That means whenever a nonlinear system is given to you, it may have equilibrium point, may not have equilibrium point. Let us see one more example to understand this concept of equilibrium point. So suppose you have x1 dot equal to minus x1 plus 2x1 x2. You can see here, as there is a product of two states, that means it is a nonlinear systems. So this equilibrium point concept, again, it is applicable to nonlinear as well as linear systems, but it is not much important in case of linear systems, because you can find, you know, that state space equation in matrix form, and from there you can characterize it. So here x1 dot equal to this and x2 dot equal to that. So for equilibrium point, what I need to do, I need to put x1 dot equal to 0 and x2 dot equal to 0. So whenever you put x1 dot equal to 0, so what you would have, that is 2x1 x2 equal to x1 dot equal to 0 means here x2 dot equal to 0 means this is equal to 0. So this is equal to 0. So that means x1 equal to 0. And when x1 equal to 0, here you can see that x1 x2 is equal to 0 and this one equal to 0. So x2 would be anything. So that means what? So x1 equal to 0 and x2 is anything. So that means whenever you draw that this is that two axes, one is that x1 axis, another one is that x2 axis. So then you can see here that where x1 equal to 0, where x1 equal to 0, so this is actually that axis. This is actually that axis where x1 equal to 0. Here you can see that x1 equal to 0 and x2 is anything. That means that equilibrium point. So you have here many equilibrium points. So in this case, basically x2 axis. That x2 axis is that equilibrium point. So many equilibrium points, but they are not isolated. That is very important. They are not isolated. So here you can see that the whole axis is that equilibrium point, whole axis, but you cannot isolate that equilibrium point. They are the continuum equilibrium points. But if you just see example 1, there you can see that example 1, there you can see that those points are actually isolated points. 0, 0, 0, pi, 0, minus pi, they are isolated points. So from these three examples, what we have learned? We have learned that what is equilibrium points. That means for finding equilibrium points, you can just put x1 all derivative equal to 0. And for a nonlinear systems, it may have equilibrium points or may not have equilibrium points, that we have seen from the second example. And also what we have seen, that equilibrium points may be isolated or may not be isolated. So they may have one equilibrium point or many equilibrium points, but they may be isolated, may not be isolated. So these are actually the information that we have obtained from these three particular examples. So let us see what we have discussed today. So we have actually in this particular lecture part, so we have started with that realization. So realization means a transfer function is given. We have to find some state space, and improper transfer function cannot be realized. Then we have taken one examples, and from here we have learned, we have defined what is phase variable. So phase variable is actually one state variable which is derivative of that other state variable. And here we have seen that one example, and from here we found that poles of the transfer function, that system, are actually the eigenvalues of the system matrix. And here we have taken one more example. From there we got two special type of structures realization. One is called that controllable canonical form, where that A and B matrices have some special structure, and the other form is called that observable canonical form, where that A and C matrices have some special structure. Now we have started with that linearization of nonlinear system, and before showing that linearization technique, here we have seen what is equilibrium points. So that means at equilibrium points, those derivative of that state should be equal to 0. And here we have discussed 3 examples. From there we found that whenever a nonlinear system is given, it may have equilibrium point, may not have, or it may have many equilibrium points, but they may not be isolated. These are actually that important results that we have seen from these 3 examples. So in the next part of this lecture, we will be just showing the linearization technique, particularly Jacobi linearization technique by using Taylor series expansion. We will be doing that one, and we will solve some examples. That means how to model some physical systems. So there we will be applying all the concepts that we have learned so far: block diagram technique, signal flow graph, state space method, etc. Okay, thank you.